Irwin, exercise 1110. A positive sequence balanced three-phase Y-connected source with a phase voltage of 120 volts RMS supplies power to a balanced Y-connected load. And the per-phase load impedance is 40 plus J10 ohms. Determine the line currents in the circuit if the phase of VAN is 0 degrees. So the source is in the Y. Let's draw that like so. And the load is also in a Y. And the load has a phase impedance of R plus an inductor. Okay, so the load is in a line, in a Y I mean, and it looks like that. Let's see, each one of those branches is 40 plus J10, and that is true for each one of the other two branches. And each one of these is 120 volts RMS. But the phase of VAN, this is A, this is B, and this is C. This one is 0 degrees according to that, so this is 0 degrees. Because of symmetry, we know that the voltage here in G is the same voltage in N, so we're going to solve exclusively this phase A of the circuit. And that is what we do. Just solve that. So we have, for phase A, only this source, and only in this load. 120, 0 degrees, these are volts of course, this is 40 plus J10. So what is that current? You say, what current is that? That is the line current, this one. The line current of phase A. That's right. Okay, that line current of phase A would be simply 120 divided by the impedance. Absolutely. 40, 10. And we do the math. That is 291 amps with negative 14 degrees approximately. Observe how I'm representing voltages and currents in polar, right? It's convenient. We see the RMS value of that current, of this one, and the phase, and that is an advantage. What about the line current in the other phases? Because after all, this exercise says determine the line currents in the circuit, so I also need to compute this one, which is the line current for phase B, and this one, that is the line current for phase C. Oh, we say that's pretty easy. That is just 291, the same RMS value for the current, but the phase is going to be negative 14 minus 120 degrees. That is negative 134 degrees. And what about the line current for phase C? Same magnitude, same RMS value, but the phase is 120 degrees past this one, would be negative 14 plus 120 degrees. You could also subtract 240 degrees, you still arrive at the same value, 106 degrees. And that is the solution to this exercise. This is the quickest and dirtiest video I have ever made, but we have a common exam, so there is no time to beautify this. Even though the exercise is not asking us to compute any power, that is actually the case very often. We need to compute the power here. Let's begin by computing the power, the total three-phase power absorbed by this load. It's a three-phase symmetrical balanced load, so we say the total three-phase power is going to be 3 times the power in one of the branches, in one of the phases. Well, let's begin with active power, P. You and I remember that active power is absorbed exclusively by resistors. So what is the power in this 40 ohm resistor? It's going to be R times the RMS value of the current, which is ILA RMS, that is over here 291 square. 3 times that is the total three-phase power, 3 times that, absorbed by the load, total three-phase power. That is 1016 watts. That is the total active power absorbed by that three-phase load. What about total reactive power, Q three-phase? Well, the reactive power is absorbed exclusively by reactive elements, in this case by this inductor. And that is 3 times the total one, X, which is 10 ohms, times the RMS value of the current, 291 squared. Those are 254 VARs. From them, using Pythagoras, we could compute the total three-phase apparent power of the load. I'm not going to do that. I leave that up to you. Use Pythagoras with those two values, and you get S three-phase. Okay, that is one way of computing that. You say, how about if we wanted to compute that power, but at the source? Total three-phase power delivered by the source. Of course, in a circuit like this one, the total power delivered by the source is going to be the total power absorbed by the load. We have only one three-phase source and one three-phase load. But anyway, let's compute the total three-phase power delivered by the source. To do that, you say, okay, for one of the phases, for this one, let's say for this phase A, I could say the total three-phase power delivered by the source is 3 times what? VI conjugate, right? Absolutely, that would be 120 0 degrees with the conjugate of this current ILA, which is over here, 291 with negative 14 conjugate, and that is 291 with positive 14 degrees. I do the computation in this corner of the screen, and when I do the math and represent that total three-phase power delivered by the source in rectangular mode, I get that the active power is the same computed as before, and the reactive power is also the same. So I could have computed that. And the next question you ask of me is, what about the root 3? We say, what about what root 3? All those root 3 formulas you showed us in class. Which ones? Oh, these ones, you say. The ones where you said the total three-phase power was root 3 V. What V? V line, absolutely. An I line for any line. Those were only RMS values, not phasors, times a power factor, cosine of something. Okay, we use those if we know V line and I line, the RMS values. We know I line, do we? I line is 291 amps. Excellent. So we know this one. Do we know V line? Let's see. We know V phase in the Y 120. V line is going to be root 3 times this V phase. Oh, absolutely. Let me write it here. V line is going to be root 3 times V phase. So that's going to be root 3 times 120. That will be 208 volts. Absolutely. So this is root 3 times 208 volts. That multiplies 291 amps. And the cosine. You say, what cosine? This cosine is actually the power factor of this load. What is the power factor of that? Let's see. Let's say the impedance triangle looks like this. 40 ohms, 10 amps. 40 ohms, 10 ohms. What am I thinking? This is the power factor angle for that one. That is the cosine of the angle whose tangent is 10 over 40. That should give me the right power. No surprise, that gives me 1016 watts. That's cool. Show the same value that I got up here. And if I use sine instead of cosine, I should be getting the 254 bars. So you see, all roads take you to Rome. You can compute that in many, many different ways. Please never forget that the total three-phase power is 3 times the power in one of the branches, and that applies for the P, for the active power, for the reactive power, and that also applies for the total three-phase power. But only if you add complex powers as vectors, eh? Okay. So I would concentrate on P and Q. Thank you very much.